Hi, you probably don't recognize me, but I'm still Old Doc Charles, and today I'm going to talk to you more about the basics of electrical engineering. And this is part 2, where I'm going to talk about volts, I'm going to talk about amps, and I'm going to talk about ohms. So to begin with, I'm going to talk about voltage. I'm going to describe what it is and where it comes from. We'll then look at current and we'll describe what it is and where it comes from. And we'll talk about resistivity, which is a material property, and it affects the resistance of an object. And we'll describe what resistance is and where it comes from. And finally, I'm going to talk about Ohm's law, which is the fundamental underpinning equation for most of what you're going to do in electrical engineering.
We have collected a load of charge together. There is a shitload of positive charge here. And there is an equal shitload of negative charge here. There is an interaction between them, which depends on the size of the charge, and the distance between them. There exists what we call a potential difference between the two charges. The formulae for this are very complicated, and if you feel you need more informations, there is plenty of good crap on YouTube. This potential difference is called voltage, it is measured in volts, and has the symbol V, or E, depending on where you were educated. Voltage can be considered as electrical pressure. There's an attraction between the two charges, as Coulomb discovered. The attraction creates an electromotive force between the charges. If an electron finds itself between the charges, it will move toward the positive charge. As shown, electrons move when a voltage is applied. The speed of the electron depends on the voltage. If the voltage is reduced, the electromotive force is less, and the electron moves slower. If the voltage is increased, the electromotive force is more, and the electron moves faster. Hello. As shown, an electron will flow from a negative potential to a positive potential. If we have many electrons, they will flow between the charges. This flow of electrons is called an electric current, it is measured in amperes, commonly called amps. The symbol is I. When 1 coulomb of charge passes a point in 1 second, 1 amp is flowing. Reducing the voltage reduces the number of electrons flowing past a point during a particular time period. Thusly, current flow is reduced. Obversely, increasing the voltage increases the number of electrons flowing past a point during a particular time period. Thusly, current flow is increased.
Basically what happens is the electrons really hop along from one atom to the next, and the electrons themselves actually move quite slowly, around about 1 millimeter per second. But the effect of electricity is almost instantaneous, and if you consider like a pipe full of water, when you turn the tap on, the water comes out almost instantaneously, even though the water itself is moving quite slowly. And another thing about current is that it's now shown or known that current is actually electrons that flow from negative to positive. But, in the oldie days, the scientists that were kind of, first doing the first studies of electricity, so that's Faraday and, Coulomb and all these old geezers, they really didn't know about atoms and how atoms worked or anything like that. So they reckon that current flowed from positive to negative. And this convention, still exists today, even though we know different. Practically, though, it doesn't really matter one way or the other, because the electrons are really too small to see. So we can say that current flows from positive to negative. There are some situations where it's important that we talk about electrons flowing from negative to positive, and where that is, I'll mention that if it's important. Otherwise, it's not important, and we can just look at the conventional current flow. Now, the current flows between two charges. It's not really practical at this point. To make electricity really useful, we need to be able to channel it into places where we want it, and we need to be able to keep it away from other places where we don't want it. And fortunately, there are materials that will help us with this situation. First, we have conductors, so that's like copper and things that conduct electricity. We also have non-conductors, also called insulators. These are things that don't conduct electricity. And we have semiconductors, which sometimes conduct electricity and sometimes not.
Hello, copper is the most widely used conductor. The reason for this is that its outer electron shell can hold a maximum of 18 electrons, but there is only one electron normally in this layer. The nucleus and the three inner layer electron layers are just represented by a single ball. This single electron is easily knocked out of its orbit by a potential difference. The atom then grabs the nearest unsuspecting electron that happens to be passing by. It takes a bit of energy to pass these electrons along. This energy heats up the atoms. The amount of energy required to pass electrons along varies for different materials. Hello, resistance is a property that impedes the flow of electrons, and uses up energy. If something moves through an absolute vacuum, there is no energy lost. This is like superconductors, which are beyond the scope of this session, so they will be mentioned no further. Now, if something moves through air at the same speed as before, some energy is needed to push through the air. This is like good conductors, such as silver, copper, and gold. If something now moves through water at the same speed as before, more energy is needed to push through the water, because water is thicker than air. This is like okay conductors, such as zinc, nickel, and iron. Now, if something now moves through maple syrup at the same speed as before, even more energy is needed to push through the maple syrup, because maple syrup is thicker than both air and water. This is like poor conductors, such as titanium, stainless steel, and manganese. If something tries to flow through a block wall now, it cannot, because block walls are somewhat solid. This is like insulators, like glass, plastics, and rubbers. However, given enough energy, even insulators can be made to conduct electricity, but it usually results in the destruction of the material. Something that now tries to flow through wax encounters various difficulty depending on the temperature of the wax. When your wax is cold, and therefore solid, it is not possible to move through it, so it acts as an insulator. If the temperature increases, the wax melts, and it can be moved through, so it becomes a better conductor. This is like semiconductors, like silicon and germanium. Their conductivity depends on temperature. Although semiconductors are used to create the modern electronical world, they are not important in this session, so will not be explained further. Now, as shown, things expend different amounts of energy moving through different materials. Electrically, this material property is called resistivity. Resistivity is the opposite of conductivity, so materials with a higher resistivity are more difficult to flow through. So there.
Okay, so The resistivity for, some common materials, for conductors, we have silver is the best conductor. It has a resistivity of 1.59 times 10 to the minus 8 ohm meters, which is, not very much. The second best conductor is copper. It's just slightly worse than silver. And then there's gold that's, again, a bit worse. And then we've got aluminum, which is kind of worse. And then you've got, other ones kind of that get worse and worse. The thing is, we use copper partly because it's a good conductor and it's a lot cheaper than silver. We use gold specifically on sort of contacts and that, because unlike the other materials, gold doesn't rust or tarnish or oxidize, whichever word you want to use. So it sort of stays the same and stays clean and doesn't become contaminated with oxides of itself, like silver, copper, and aluminum can do. And then for insulators, they've got sort of a wide variety of resistivities depending on the actual material. So for example, glass has got a resistivity of between 1 and 1 times 10 to the 21. So it's between 8 and 30 orders of magnitude greater than silver. And then you've got quartz, which is fairly constant. And then depending on the type of rubber, again, a wide variety in resistivity. And the same with plastics. Now wood also has got quite a wide value for resistivity. It's partly due to the type of wood, and it's also partly due to the fact of how wet the wood is. So if your wood is quite wet, it's going to have a much lower resistivity than if you've got dry wood. And the same with air. Really, it depends on how moist the air is. So if your air is very moist, it's going to have a lower resistivity than if your air is quite dry. All right, so that's the various resistivities.
Hello. As shown in a previous film clip, resistivity is the material property that determines how difficult it is for electricity to flow through. There is more to this resistance bollocks than just resistivity. The dimensions of the material are also important. For example, length is significant. If the electrons have further to go, they expend more energy. Just like anything else. To go twice as far needs twice the energy. Cross-sectional area is also significant. For a given current, the smaller the cross-sectional area, the faster the electrons must travel, so they need more energy. If the cross-sectional area is halved, the electrons must travel twice as fast. Now, what this means is that a material of a certain length and cross-sectional area will have a resistance, R. Resistance is measured in ohms, and the symbol is the uppercase Greek letter omega. So there.
Right, so here we have 4 different bits of metal, and there's 2 different types. There's a coppery one, colored one, which is copper, and the silvery one is aluminum. And you can see they're all different diameters and different lengths. But the one thing they all have in common is they all have the exact same resistance. So the resistance of a material really is the resistivity times the length divided by the cross-sectional area. And that's what gives you the resistance in ohms of a particular sample.
Hello. When a voltage is applied across a resistor, a current will flow. More current will flow if the voltage is increased, and conversely, less current will flow if the resistance increases. there is a linear relationship between resistance, current, and voltage. This relationship is referred to as Ohm's law. Ohm's law simply states that the current is equal to the voltage divided by the resistance. An easy way to remember the relationship is by using Ohm's law triangle. Putting V at the top, and I and R beside each other at the bottom. To solve for one of the variables, simply cover the variable you want to know, in this case I, and the formula is then what's visible, V over R. The same goes for the other variables. V equals I times R, and R equals V over I. So there.
Right, so to kind of recap that bit, electric circuits really can be described by a voltage, which is volts, and it's produced by batteries and generators and fuel cells and solar panels and all sorts of weird things nowadays. And it's the electrical equivalent of pressure, and it's what actually supplies the energy to the circuit. The current is in amps, and it's the flow of electrons in a circuit, and it's the electrical equivalent of fluid flow in a pipe. And the resistance in ohms is what opposes that flow of current. And the relationship between these three is linear in sort of basic circuits. There are situations where the relationship isn't linear, and we'll talk more about those later, because they're important in sort of various other places. But yeah, we'll talk more about that later. And Ohm's law's triangle is the easy way to remember the relationship. Volts is equal to amps times ohms. So to recap, voltage is a difference in charge separated by a certain distance. Voltage is the electrical pressure that pushes a current. And current is the flow of electrons moving from negative to a positive charge. And resistivity is a material property that describes how difficult it is for a material to conduct electricity. And resistance is proportional to resistivity in length and inversely proportional to the cross-sectional area. So that about wraps up for this part 2 on volts and amps and ohms. And join me again for part 3 on something or other, electrical. And yeah, until then, yeah, I think that need be all. See you. Bye-bye.